So in the previous video we saw how we started from the shearing size we identified the interesting regions, and then we analyzed them, the reads from the plus and the negative strand, and we got the fragment size. And let's say that this fragment size is 250 base pairs. Now what is next? Then we form a window of 2 times this fragment size, so we have a window of 500 base pairs, and we take this window and we slide it over the genome. So I will use this yellow color here for the window. And again, on this window, we will measure how many reads we find. So let's say that in this one we find 35 reads. And then we move this window 1 position to the right. I'll use another color. Yellow is too light. And we measure again the reads. Let's say that this orange window contains 41 reads, and so on and so forth. So again, we get now reads, but actually now they are contained within the correct fragment size, 2 times the correct fragment size. So we'll have these numbers: 35, 41. Let's say that we'll have 51, and then 36, and then 7, and 6, and 5, and 4, and 21, and 23, and so on and so forth. And let's also assume, so this is the ChIP experiment, and let's assume that we do the same in the input. So we have the input here, which also has some reads, so on. And if we can count now the reads here, it will be, let's say, 7, 6, 5, 4, 3, 4, 5, 8, 20, 22, and so on. Okay. Now let's see what is the process to find significant windows. So the first part in the previous video we had the term interesting windows, and now we will do a statistical analysis on that to find significant windows. These numbers comes from the ChIP sliding window, and this for the same window size, so 500 base pairs, we had a window of 500 base pairs, and we slide it along the genome and we found these reads. And for the input, we slide the same window and we found these reads. And we want to find windows that have more reads compared to the rest of the genome, but also more reads compared to the input. Okay. So our first goal will be to compare this number here to the rest of the genome. So this one has 35 reads, and the average of all other windows, let's say that is 8.5 reads. Okay, and now we come to the statistical analysis one. If we assume that all windows here come from the same process, so the number of reads in all windows come from the same process, then this process would be a Poisson distribution with parameter lambda, which is the mean of the Poisson, equal to 8.5 reads. So this means the following, that if we would have a window of 500 base pairs, then on average we would expect 8.5 reads in this window. So this would mean that comparing, if we would assume that every window here, every number of reads in a window come from the same process, which this is our null distribution, this should be a Poisson process with 8.5 reads on average. And let's call it lambda background, because it compares, it tries to obtain insights into the random process that generates the number of reads based on the whole genome background of a window, so of the ChIP genome. Okay. Now, if we compare this window with the respective window on the input, again these are 500 base pairs, we said that we will have severance here. So our second guess would be that there is a random process, a Poisson process, but on average this one produces 7 reads, because 7 reads is what we see on the same region in the background. So let's call it lambda region is 7. Now again, this is by using the genome background of the ChIP. So all other windows except the one that we are working with. And here it uses the same region on the input. Then MACS is taking two other windows. One is yeah, it's better to draw it like that. So if this is again the ChIP, and this is the input, and here we study this window, and here the same window, 500 base pairs, and here we have 500 base pairs again. Then we take the middle of this window, and around it we take a region of 1000 base pairs. Now, okay, here we are a bit unlucky because we are at the edge. Let's say that we are not at the edge. So 100 base pairs around it, we will go from here to here. And using the reads that we have in this region on the input, now we said in the beginning, we said previously that we have in the input 7 reads in the same region. So let's say that inside here we have 7 reads. But in all this 1000 base pairs region around the center, we might have, let's say that we have 30 reads for some reason. So this means that we have many reads here and many reads here. Now this means the following, that in a region of 1000 base pairs, we have 30 reads in the input. which means that in a region of 500 base pairs, we would have 15 reads. In other words, we use a bigger region around the center of the window to try to understand how many reads we might have in a general region on average. So this is 15 reads per 500 base pairs, or 30 reads per 1000 base pairs. Which means that our best guess for the lambda, using as information a bigger region, not just the window, would be that lambda 1kb, let's call it like that, would be 15. Okay, so up to now we have three values of lambda. We have the lambda background, which we calculate to be 8.5 here. We have the lambda region, which is 7, because in the corresponding reads in the input we have 7 reads, and we have the lambda 1kb, which is 15, because in the 1kb region around the center of the window in the input we have 30 reads in 1000 base pairs, so which means that in 500 base pairs we would have 15. Okay, and we do the same process with two other regions. One will be 5000 base pairs, so we should go further. Now let's say that in this 5000 base pairs we would have 100 reads. This would mean that in 500 base pairs we have 10 reads on average, which means that the lambda 5k would be 10. And we do the same for a region also 10,000 base pairs. And let's assume that in these 10,000 base pairs we would have 220 reads, which would mean that in 500 base pairs we would divide this by 20 and this by 20, and then we would have 11 reads, which means that the lambda using the 10kb information would be 11. Okay, now we have several lambda values. Let's write all of them somewhere. We have the lambda bg, which is 8.5. We have the lambda region, which is 7. We have the lambda 1kb, we just call it lambda 1, which is 15. We have the lambda 5kb, which is 10. And we have the lambda 10kb, which is 11. Now, if we want to be conservative, we might think the following. Okay, in reality, in our region of interest, we have observed 35 reads. I will write it here. We have observed now we might think of a random process that has generated these 35 reads, but this random process might be any one of them. So it might either happen that we have 35 reads and this is a part of the background, or because the region is interesting, or because around 1 KB of the position there are many reads, and so on and so forth. If we're going to be conservative, so being conservative means that we don't want to think so easily that the region is interesting. We don't want to think so easily that this region with 35 reads is a region that corresponds to a real peak, to a real binding of a transcription factor, but has been generated just by chance by one of these processes. If we want to be conservative, we will think that this region with the 35 reads might have generated from the process that has the highest lambda. And the process with the highest lambda is this one, because 15 is greater than any one of them. Okay, so we take the maximum of them, and let's call it lambda, is 15. So now we say that, you know what, the region with 35 reads here is nothing interesting, but it is the outcome of a random process which has lambda 15, and this random process is a Poisson process, described by a Poisson distribution. With lambda equals 15, and this forms our null hypothesis H0. Okay, now let's see how easy it is to take 35 reads from such a process. Now the Poisson distribution, as you know, is a discrete distribution, and the average of this will be on 15. Then it will drop like that. Okay, now if we go to internet here, we write Poisson online applet. We have lambda 15, which is this distribution, so you see that the peak is at 15, and then we might have, just by chance, generated 21, 22, 23 successes according to this process. Now if we want to find the p-value of having observed 35, how many we had? 35, I think, right? Yeah, 35 read or more by chance, we go here, just put a number 35. Sorry, here, 35. So the probability to observe 35 or more reads by chance when the Poisson process has a lambda rate or average value 15 is just 0.00001, which means that if we would assume that this region, this interesting region here, is just a result of chance that just got more reads without actually being a transcription factor binding site itself, then the probability to obtain 35 or more reads just by chance would be this small number, 0.00001, which means that we reject the null hypothesis. So we reject the hypothesis that states that this region is just a matter of chance, is not an interesting region, is not a region that a transcription factor binds. We reject that, and we accept that this region is in fact an interesting region, a significant, as we said, region, significant region. So with this way, we might classify each region of these 500 base pairs. So this is one region, this is another region, next to that, next to that, as either significant, and let's use the number 1 for that, or non-significant, let's use the number 0 for that. So we'll have something like that. Significant, 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 non-significant, and so on and so forth. And if there are many regions that are significant next to each other, we will all group them together as one big region, that corresponds to a transcription factor binding site. Now, this region does not have 500 by 3, so this region is 500 base pairs, the first one, so this one. But the next to that is overlapping with the first one, so, and this one is overlapping. So if this step from one region to the other is just one base pair, now the fact that we have 3 consecutive ACs would mean that this region would be 502 base pairs long. And this region is a transcription factor, is a region that MACS identifies as significant, so it's a region that has a peak. And for MACS, it corresponds to a transcription, to a binding site for the protein, binding site. Okay, so this was the second part of the talk about how MACS works to identify significant regions.